Hi, what we are going to do in today's video is try to measure temperature using Commodore 64. Now, if you already seen this or read about it or have already done it yourself, there is high probability that sensor in question was analog temperature sensor, or better say thermistor, connected to analog pin to one of those two joystick ports that we have on Commodore 64, which is absolutely fine, works great, and it's a lot of fun to play with that, but we are not going to do that today, no. What we are going to do is connect digital temperature sensor to our Commodore 64, and matter of fact, this digital temperature sensor, and this here is DS18B20 digital sensor. It's very common sensor, very cheap, and we can measure temperatures from minus 55 degrees up to 125 degrees Celsius with it. It has precision of plus minus 0.5 degree Celsius, which is good enough for our little project here. And this one came in this probe package, which means that is waterproof, and that means that we can measure temperature of liquids, which we are going to do in this video, and it uses one-wire protocol for communication. So what we will need to do is see how can we hook up this sensor to our Commodore 64 to see how one-wire protocol actually works. Now, one wire stands for one wire. There is only one data line, one wire for communication between the host, which is going to be Commodore 64 in our case, and device on the bus, which is going to be this temperature sensor. Also, each of these one-wire devices has his own unique address. That means that we can have multiple devices on one wire, and that's very, very handy. And beside that one wire for data communication, we also need one wire for the ground and one wire for power. In our case, it's going to be plus 5 volts. Also, one wire bus or one wire protocol has one special mode. It's called parasite mode, where we actually don't need that plus 5 volts power line. We only need ground and data line. That means just two lines. We are not going to take a look at that type of mode today, but just for you to know, that's also possible. And because there is only one wire for data communication, that means there is no clock between the host and the device. There is no method of synchronization. That means that we are going to depend on the timings, and that means that BASIC is out of the question. C, I haven't tried, and that means that language of choice for today's video is going to be assembly. Yeah, we will need to be very fast with this little fellow. Like I mentioned, it's digital communication. We will need some digital GPIO pins, and Commodore 64 has 8 of them. So what we are going to do is connect this device to user port on Commodore 64, and I will use this little development board to help me connect everything together. And we will start with hardware. We will start with explaining how to hook up everything together, and then we will switch to software and see what do we need to make this communication possible. So yeah, let's begin. Okay, and this is our hardware. So this here is our little sensor, and we have 3 wires coming out of the sensor connected to this PCB, and this PCB has this user port edge connector that goes into our Commodore 64 user port. And now it would be great time to mention that this video is sponsored by PCBWay. So if you need good quality PCBs, well, PCBWay is the way to go. Just visit PCBWay.com and get great quality PCBs from just $5. It's very easy to place your order and you get your PCBs delivered for you very quickly. And beside PCBs, PCBWay offers the whole palette of other services. But my favorite one is the shared community projects, where you can find all sorts of projects already prepared and you can order them with just one click of the mouse. And this is how I got my Commodore 64 user port development PCB. Just visit PCBWay.com. These are user port development boards that I got from PCBWay.com. They're very good quality and very nicely built. So yeah. And what else do we have here? Oh, we have those beautiful rulers. Yeah, where is it? And we have a little bag. Yeah, we have this and we have a pen. Yeah, that's always nice to have. And what do we have here? Well, let's go. Oh, PCBWay logo. That's nice. Ooh, this will be beautiful project to put some LEDs on this. Yeah. So back to our project and see how did we use this PCB. And yeah, so that's how I got this this development board. And beauty of this development board is well, you see all of these pins on our user port, top one and bottom one from both sides. They're all available here on our PCB. You see, all of those pins are available for us on this side, but also they're available on the other side of the PCB as well. So yeah, very convenient, very nice, nicely built and nicely designed. So I really like this development board. There's plenty of room to build any kind of project, so very nice. And also the benefit of having a PCB, well, of course we could connect these wires directly to our edge connector, but having a PCB, well, it's easy to plug it in and unplug it. And that's the most important part. And usually I always have a problem when I connect the wires directly to edge connector. Well, when you connect everything to user port on Commodore 64, most of this connector is located inside the case and it's very difficult to unplug it. So yeah, having this little board, it's very easy to unplug it without damaging the wires and rest of the connections. So yeah. And what we have here, like I mentioned, 3 wires. One wire is this is yellow wire, usually is the yellow one, which is data line. So this is the line for our communication, and it's connected to pin D here. Of course, D is PB1, so that's one GPIO pin out of the 8 of them that we have available on our user port. And it doesn't really matter, I choose this arbitrary. I could choose any of those 8 pins. And then we have red wire, which is power line connected to plus 5 volts on pin 2 on user port, and the black wire is of course the ground connected to pin number 1, which is the ground. And we have one pull-up resistor between data line and the power line. The values for this resistor is usually from 3 up to 5 or 6, 7 kilo ohms. It doesn't have to be specific value as long as we have weak pull-up link. So that means that this data line is by default pulled to high. That's it. And there is nothing else here. It's very simple to connect it. So as you can imagine now, most of the work for the one-wire protocol will be done in software. So yeah, and now it's good time to switch to software part, or to be precise, assembly code. Okay, so before I actually show you the code, we need to know how this one-wire communication actually works. In one-wire communication, everything is initiated by the host, and a host in our case is Commodore 64, and our little temperature sensor is the slave device. So we have to do all the work, and you will see how that is done. Also, one-wire protocol communication is done bit by bit. So that means if we are writing something, we are writing bit by bit. If we are reading something on the data line, we're reading bit by bit. And you will see, like I mentioned before, it's all about the timings. I will show you a couple of timing diagrams because that's the easiest way to understand how this protocol works. First of all, this writing and reading cycles takes up to 120 microseconds. So that's one cycle. That's the time period for reading or writing a single bit. And what we have here in case of if we want to write a logic 0 to our one-wire bus, well, first a host or Commodore 64 will pull this data line low, and it will remain low for about 15 microseconds. And after that, if we want to write or send logic 0, we remain low with this line in total 60 microseconds. So this whole process, just pulling the line low for 60 microseconds, and after that we release the line. That means that we want to write logic 0 to our bus. In opposite case, if we want to write a logic 1, well, we keep that initially that line for 15 microseconds, we keep it low, and after that we pull that line high. And again, this whole sequence here should last about 60 microseconds, and the whole cycle again 120 microseconds. So that means that we are writing logic 1 to our bus. So you see, it's almost the same procedure except for the timings. They are a bit different. And how about the reading? Well, it's almost the same. So if we want to read, again, a reading process takes again 120 microseconds in total for a single bit. And the host initially, again, the host is the one that initiates the reading, pulls the data line low for not more than 5 microseconds. And after that, we have to release that line. If the line goes high, then we can read, then we know that we received logic 1. And if the line remains low, then we receive logic 0. So that's the whole protocol. That's it. There are a couple more things, but yeah, that's initially the basics of one-wire protocol. It's very simple, but again, we depend on these timings, and those timings are crucial here. So we are talking about microseconds here, so yeah, we need to be fast. Also, there is one more procedure between any kind of operations. We have to reset the one-wire bus. And again, it's quite simple. We pull this line low for 480 microseconds, and then after that we release that line. And if our slave device, or in our case temperature sensor, is active on the bus, it sends back the acknowledge signal. In the next 480 microseconds we should receive the answer from our little sensor by pulling this line low. And then after that the line is released. And you will see in my code that I spend a lot of time just fine-tuning the timings and try to figure out which is the best way to implement something. And yeah, you will see in a second. So yeah, that's it. So let's go finally to our assembly code. Okay, and finally we are in our assembly code, and just a little warning, this is not the optimized code, this is my development code where I experiment a lot with those timings and everything, and in a certain point this was complete mess of the code. So yeah, Keep in mind that. So okay, at the beginning we have a couple of variables defined. I mostly use zero page memory, so that's all. And then we have a couple of these kernel routines, and we have registers for our GPIO pins, or better say that's port B on user port on Commodore 64. So yeah, and then we have a couple of more variables, and these are to convert our 16-bit raw value to floating point degrees Celsius, so real temperature, and I will explain that later. This is not proper floating point arithmetic. This is my little mess that I made. So this is where our main program starts. So let's clear the screen at the beginning, and then we are storing hex value 1 to certain position in a zero page memory. We will use this to send bits. I'll explain that later. And then we configure our GPIO pins to be output pins. We set all the pins, all 8 of them, to be output pins, which is okay because we are not using those pins for anything else at the moment. And because we are using just PB1 GPIO pin, maybe the proper way to do this should be to load first current configuration of our pins, and then just change the value for the pin that we are interested in, and that's PB1. So that should be 02 in hex. That means that we have a 1 2 3 4 1 2 3 4, and this is 2. So we are going to activate or set only the PB1 pin to be output pin. Everything else should remain as it is, and then we need to store that back to our register. Yeah, maybe that should be a proper way to do this, but okay, whatever. And then we have our main loop here. Okay, so what we are doing in this main loop is just initiating the temperature measurement on our sensor and read 16-bit raw value out of it and convert that to real temperature in degrees Celsius. That's it. And we are constantly looping over and over again. So at the beginning we first have to send that reset signal, and after that we just make a little delay, and then we call this subroutine called select device. Like I mentioned before, on one wire bus we can have multiple devices, and each of these devices has its own unique address. So if you want to communicate with a specific device, you need to first select it by its address. Now we have a specific situation where we have just one device on the bus. We just have to tell that we want to speak with that device. So the select device subroutine is this one here. Now if we send opcode 33 in hex, and we do that right here, what we are going to get is the address of that device, and this device now will be selected for communication. If we had more than one device, this part would be more complicated, but for now it is as it is. Now back to our main loop. So after we select device, we have to initiate the temperature measurement. So we do that by sending 44 opcode in hex to our device and waiting a little bit time so that this little sensor can perform its measurement and store those values into memory. Now this part of the sequence is done, and we have to send the reset signal again. And again we have to select device, so all over again. But this time, instead of initiating temperature readings or temperature measurement to be precise, now we can read those values back from the sensor and get a 16-bit raw value out of it. So, and we are doing this by calling this subroutine called read scratchpad. That subroutine is right here. Now let me explain what the scratchpad is. So the scratchpad actually is nothing more than, and what scratchpad is just a memory in our sensor that we are allowed to read from and write to. I didn't mention it so far, but this sensor can be configured a little bit differently. So, and I didn't go into that part in this video. We just use it in default settings, in default configuration as it is. But as you can see, our scratchpad, or that sensor memory, is containing 9 bytes, and we have to read all of those 9 bytes. But of course you can see that our temperature values, or least significant byte and most significant byte, are at positions 0 and 1. So the first byte and the second byte will be the values that we are interested in, and those that will be our 16-bit raw value. Also, what we care about, and we care about very much, is the checksum. So the last byte in this package is the checksum value, and we need to read that, and we will calculate our own checksum. And you will see I have a subroutine that calculates the checksum for the first 8 bytes of this package and compare it to the checksum that we received from the sensor. If those two checksums are equal, then we are good to go. We have correct values. If not, yeah, there's something wrong happened. Like I mentioned before, we read all 9 bytes in this loop, and then we are calculating our checksum from the first 8 bytes and comparing it to the checksum that we received from that little sensor. If everything is okay, we will continue to convert that 16-bit value to real temperature in degrees Celsius, and this code here, everything here does exactly that. But I will skip this for now. I want to show you subroutines for reading and sending bits, and then I will come back to explain this part as well. So yeah, this is how we read entire byte, just reading 8 bits. Well, if you're wondering why didn't I use just simple loop here instead of this repetition, well, in case of a loop, I have lots of incorrect readings, so that means the timings are incorrect, there's something wrong. So the fastest way is just call this subroutine 8 times, and after we read all the 8 bits, we just store it in this address. Again, this is address in 0-page memory, so yeah. Okay, so let's see how do we send the byte, because well, we are sending bit by bit, but we have to send the entire byte. You saw earlier that we are sending opcodes that are 8-bit values, right? So what we're doing, whatever byte that we want to send, first we load it into accumulator. What's happening here is we need to send bit by bit, starting from less significant bit to the high significant bit. So we are sending from bit 0 to bit 7. And I'm using this bit instruction, which is a bitwise comparator. So that means that this bit will compare whatever value is in this variable, in this memory address and 0 page, and compare it to value in the accumulator, and the result will be stored in carry flag. So that means that our value in accumulator will be intact, and that's the most important part here. We don't want to do any kind of bitwise logic here that will destroy our value, right? And if you remember from the beginning, the value of this variable is, where is it? Is 1. So we are just comparing the last significant bit in the accumulator with value 1. So we are interested to see whether it's 1 or 0. Okay. So where was I? Yeah. Okay. Here I am. So if our carry flag is triggered, so that means that we have high bit or bit 0 or bit 1, sorry. And then we are sending high bit signal, which is subroutine right here. If not, then we are sending low bit, so we are sending low signal. And after that we are just roaring the accumulator. That means we are rotating to the right, so we are shifting to the right our accumulator, and every time that we send least significant bit, we send it out to the one wire protocol, then we shift it out of the accumulator, and so on until we send all the bits from the accumulator. That's it. And subroutines for sending bit, high bit and low bit are right here. So to send a high bit, we just pull our data line low. We immediately after that we release that line, and then we just have certain delay. So maybe these values are not completely correct because all of my experiments, but everything here counts. Even this return instruction takes some time, and everything has to be taken in consideration to calculate all these timings. And if I change the position of this subroutine in the code, maybe the code wouldn't even work. So yeah. And then if we want to send a low bit, we behave a little bit different. It looks completely the same, except the timings between the pulling the line and releasing the line are different. So this time we pull the line low, we wait just a little bit time, and then we release it. That's it. So we are sending 0. So how do we read the bit? Well, almost the same procedure. We pull the pin low, and after that, immediately after that, we are releasing that pin, or we are setting it high, and then we have these 3 nope instructions. That means that we are making just a small delay here, and after that we are reading the state of that line and compare it. Do we have high state or the low state? If we have high state, then we received bit 1. If not, we received 0. And what I'm doing here is if I receive 1, we are loading this address, 0 page memory address, which should contain in the end the entire byte. So we're loading that, whatever the value of that is, we are shifting that to the right. So we are making room in the most significant bit, and then we are ORing that with hex value 80, and hex value 80 is in fact 10000000. So we are adding bit 1 to our most significant bit. So that's it. And then we are storing back that value back to our 0 page memory with this address here. The same happens if we receive the 0, just this time at the most significant bit, we are, instead of 1, we are storing 0. Now, if we repeat this process 8 times, because we're receiving 8 bits, every time this will be shifted right, and in this place this last significant bit will drop out, and in this place this will be 1 in case that we receive 1, or this will be 0 in case that we receive 0. So we will have something like this, and every time that we receive a new bit, everything here will be shifted to the right, and we will store a new bit in this position right here, whether it's 1 or it is 0, right? So that's how we read bit by bit, we read entire byte. So back to our scratchpad. So okay, we read entire scratchpad, we receive all the bytes, we compare the checksum, everything looks good. Now it's time to convert that 16-bit raw value in real temperature in degrees Celsius. And now we have to know what this 16-bit raw value represents. Now if we take a look at the datasheet for that little sensor, it simply says if we divide that 16-bit raw value with 16, decimal number 16, we should get real temperature in degrees Celsius. Now the easiest way how you can divide 16-bit value or 8-bit value in assembly with 16 is just to shift everything right for 3 places. If you do that, the result will be integer, of course. It will be either 8-bit or 16-bit value, but the whole number, and it will represent degrees Celsius, except we will not have decimal places, right? We will not have floating point number. But here I really want to have floating point number or decimal number, real number, and before we even go into that section, we also have to know that this 16-bit raw value is actually 2's complement. So that means that it contains negative and positive numbers. So first we have to deal with that. What do we do here is just compare whether or not our 16-bit value is negative or positive. In case that it's negative, so we are measuring negative temperature, all we do is we are printing the minus, Petsky character minus, on the screen. That's it. So, and the rest of the way we will convert this number to positive, and we will treat it as a positive integer, 16-bit integer. That's it. So after this we have just a regular 16-bit value, and now instead of that shifting, what we are doing is I have a little subroutine that will divide two 16-bit numbers, and the result will be again 16-bit value, 16-bit number, the whole number, integer. We are not talking about floating point numbers here, we're talking about regular round integers. So still we will have, the result will be integer, and that will be the whole part of our real number, so the whole number in degrees Celsius. But also what this subroutine will give us is the remainder of that division, and that's very important because we are going to use that remainder one more time. And first of all we are going to multiply that remainder with decimal 10, that is this 0A in hexadecimal, and after we multiply it with 10 we are going to divide that number once more with 16, decimal value 16. And this here is that division by shifting. So we are shifting that number 4 times to the right, and it's the same as we divide that number with 16. And this time there is no remainder, but what we get is the first number, or better say first 16-bit value behind the decimal point. So the result will be 16-bit number. And what we are doing next is, first we are going to display the whole part of the number, the whole part of our temperature. Then we are going to print out the dot as pesky character dot, and then we are going to print out the decimal part of that number. That's it. Very simple, very elegant. Of course, this decimal part again will be a little bit rounded. And this is the whole code, this is everything. And now it's the time to test this code and test our little board and our little sensor, and try to do some experiments as well. Yeah, because I want to show you how those negative temperatures looks like, and yeah, we want to see some changes in temperature. Yeah, okay, let's do that. So here we are, our sensor is connected to user port on Commodore 64, as you can see here, and we have software ready, everything is prepared for the first tests. So let's start our code and see, do we get measurements? And we do. Here we go. Now let me hold that in the hand and see, will it warm up? And it does. Let's release it. Okay, now we can see those values a bit better. Yeah, here we go. Okay, and what do I have here is a little bit of ice. So let's try to put this little probe into ice and hope that we can go below 0. So yeah, try to do something here. Oh, come on, let's go below 0. Oh, we are going fast. Five, 4, you're getting close. Let me show you here. Yeah. Oh, cannot see anything here. Maybe 2, 1, 2. Come on. Come on. Come on. More below 0. Come on. Okay, minus 0.03. Okay, okay. Yeah, and we are below 0. And what I'm going to do now, I'm going to prepare a little bit of hot water. Okay, what I have here is a little bit of hot water. So let's try to do this. Oh, we are going fast. '65, 67, 70 degrees. How about 80? Yeah. And now back to the ice. And we have a glitch. Okay, that's nice. And what we are going to do now we are cooling down. And now I'm going to pour I mean, I have Commodore 64 and water just beside it. This is not a very clever thing to do, but I'll try that anyway. So pouring hot water into ice. Our water is getting colder. Okay, so the test that we perform here has no scientific meaning whatsoever, so that's just good to know. Okay, yeah, and this is all that I have for you today, so until next time, goodbye. Okay, I'm not sure if this will work or not. Will it broke the sensor, but I frozen the sensor inside the water and ice. And what I'm going to do now is try to measure temperature. Yeah, now we are below zero. Minus 1.1, 1.0, minus 1. Okay. Yeah, that's below zero.